As mysterious as they appear, our knowledge about black holes seem to be as dark as how they are pictured to be. That's why we're taking on the 6 most frequently asked questions about black holes in today's episode. I think none of us here haven't heard about black holes, right? It's basically a great conversation starter and a plot device for a lot of science fiction. It's like one of the great things that gets you interested in exploring the field of astronomy. And I wouldn't blame you at all. I mean, it's pretty easy to get amazed by how extreme, how bizarre, and how mysterious black holes are. If that doesn't get you to be attracted to, let's say, science at the very least, I don't know what will. Maybe some dinosaurs? But as majestic as they come, there's really a lot that we don't know about it. Even the scientists who study these kinds of objects still have a lot of questions, and each time they try to answer them, they end up with more questions. It's a crazy Russian doll. That's why today, why don't we both get down to the bottom of it all? Let's talk about the 6 most asked questions when people talk about black holes. Number 6. How do we make black holes? Okay, to set the pace, let's get this going with something very basic and simple. The origin of a black hole. If we're going to talk about something, it's one of the best places to start, right? In theory, anything can be turned into a black hole. All you have to do is compress the volume of the object into what's called its Schwarzschild radius. Easy. But okay, let's get real. We know that we don't have that amount of force. Some of us here can barely open a can of pickles, let alone have the capacity to crush an object to an infinitesimally small size. So instead, let's look at where there is an abundance of it. Where else but space? Like its equally extreme cousin, the neutron star, black holes can be thought to be some sort of stellar phoenixes. They arise from the ashes of another dead star. While technically speaking, they didn't arise out of nowhere. They're the former nucleus of that other star. It's like if a heart of some human comes out of its body and decided it wanted its own life. If you know Ricardo of Adventure Time, you'll know what I'm talking about. Okay, that's too much tangent. So let's discuss how exactly an old star gives birth to a black hole. Stars undergo their own respective life cycles. It starts as a cloud of dust particles, to a young star, to a giant, then it goes into its inevitable death. So basically, a star fuses hydrogen most of its life, but once it runs out of hydrogen, it goes off script and begins fusing helium. And running out of that, it starts to fuse heavier elements instead. Now you may think that's nothing to be afraid of, but when you fuse heavier elements, you expect to generate more energy. This energy generated by fusion battles the gravity that's been trying to crush the star, until the balance tips and gravity wins, resulting in a massive bright supernova. Whether or not it ends up as a black hole normally depends on how massive the star was. On one hand, the core could collapse to a neutron star. On the other hand, if it's too massive, it becomes a black hole. According to studies, the bare minimum mass range to determine whether a star will collapse to a black hole or not is around 3 to 5 times solar masses. Actually, it is guaranteed that if a star's mass falls in that range, expect a black hole at the end of its life. Number 5. How can a black hole pull light? If you have studied quantum mechanics, one of the characteristics of light that you might have heard is how the particles of light, photons, are actually massless by the common convention. And the kind of force that black holes use is exactly gravity. From the basic definition of gravity, we know that for something to have this kind of force, it's got to have mass. An object with extreme mass sucks in a massless object. How exactly do black holes accomplish this? First, let's explore a theory first brought by Einstein: general relativity. Specifically, the most important part of it, which can help us understand how black holes work. Newton established gravity as some sort of non-contact force. It acts from one object to another event without contact. However, our hero, Albert, remediated this by explaining how gravity isn't really an eerie force transmitted without contact, but is actually a distortion of space-time by massive objects. Think of it this way. Let's say we have a trampoline, and that nobody is jumping up and down on it. You expect the trampoline to be flat, right? But for instance, we place a gigantic rock anywhere on it. That area gets pushed down. effectively making some kind of bowl around the rock. If you place a marble anywhere on the surface of it, you would expect it to roll towards the rock, right? That's how gravity actually works, according to Einstein. Now let's go back to the black hole. Since gravity is a distortion of space-time and black holes exerts possibly the strongest gravity we can expect in the universe, then it just makes sense that light will have no choice but to bend as well in the presence of a black hole, right? Think of it this way. If you're in a bathtub and you apply force to one of your rubber duckies such that it moves to a specific direction, then you open the drain, the duck will technically still be moving at the pace you set it to. It's just that it experiences a stronger force distorting its motion. Who thought something as extreme as black holes can be explained using rubber duckies? Number 4. What's the biggest and smallest a black hole can get? Well, I think the first thing and the easier thing we can answer here is how large can black holes get? According to astrophysicists, theoretically speaking, there isn't a limit to how big black holes can get. But let's talk about what currently holds the record in terms of being the largest we currently know. In the center of every galaxy, it is expected that we will find something that we call a supermassive black hole. It is estimated that one of these can have a mass of 1 billion suns. I know what you're thinking. If this is what holds the record as the largest kinds of black holes, what's the largest supermassive black hole that we know to date? We're going to answer that, but I want to know what you think of the show first. Love it or hate it? Leave us a like if you believe the former, and a dislike if you think the latter. Any feedback from you helps build a better show, and a better channel for that. So okay, back to the question. What's the largest supermassive black hole on record? The current title holder is M87, a supermassive black hole with a mass of about 40 billion suns, with an apparent size of about 9.5 trillion kilometers. Even if you travel at the speed of light, it could take you more than a year to travel that diameter, assuming you won't get torn to pieces by the gravity first, that is. How about now we explore the other end of the spectrum? What's the smallest size a black hole can get? Of course, this one is a bit more harder to find, since faraway objects have to be of a certain size for us to be able to observe it from Earth. But as per recent studies, it is hypothesized that a black hole can reach no smaller than 10 to the negative 33 centimeters. That's way smaller than a proton. Number 3. How does time work in a black hole? If you watched the movie Interstellar, it's most probable that you have stumbled upon the crazy scene when the crew was near a black hole. For those of you who haven't seen it, there were a few scenes where time was severely depleted from the characters as they were near a black hole. Going down to a planet close to it cost them more than 20 years, even though in their experience on the planet, they only stayed for about an hour. Pretty crazy, right? It's like you went to Taco Bell for a quick bite, and then you come back and your kid is already finishing a postgraduate degree in economics. So obviously black holes have a way of messing with time. But how exactly does this work? Well, the answer can again be derived from arguably Einstein's best work, general relativity. Remember earlier how we established that gravity is more than just a non-contact force and that what it essentially is a dent-forming entity in space-time? Let's work from that analogy. If you pay close attention to the word space-time, then the answer is already there. Special relativity tells us that as you move closer to the speed of light, time goes by faster for everybody else outside. Let's extend that to gravity. Gravity effectively stretches space-time. This is why one step near a massive object on the fabric of space-time definitely is longer than a step far from it. In simpler words, as you get nearer to a black hole, time slows down. And in the spirit of that question, we move on to the next. Number 2. What happens when you fall inside a black hole? Let's play the role of God here, where we have the entire universe as our sandbox. Let's create two persons, which we will call Pauper and the other Copper. Let's protect these two guys with the perfect material, in such a way that they won't be harmed in space. And also let's make their visions perfect, such that whenever they see will be extra clear. Now let's create a black hole. Copper and Pauper tossed a coin, and Pauper won, so he got to pick where he wanted to be. In this thought experiment, he chooses to travel inside the black hole. Copper, on the other hand, we place on a safe point where he could see Popper falling into the event horizon. Let's take Copper's perspective first. How does he see Popper as he falls straight into the black hole and crosses the event horizon? Since the force from the black hole will be so powerful, you expect Popper to fall really quick, right? That's not what happens, however. The photons coming from Copper will be relatively slower as compared to his descent to the black hole. So what happens is, as he falls in, Copper sees Popper falling extremely slowly, as his time is also slowing down, as he's falling faster than the photons could reach the other guy's eyes. Later on, Popper would turn red as a result of Doppler effect, and then his image would simply freeze. Copper would witness Popper's image suspended as it becomes dimmer and dimmer, until it completely disappears. Freaky. Now let's take Popper's perspective. What does he see as he falls into the black hole? He still sees Copper at a distance, but since he is falling at a crazy fast rate, his eyes only receive a finite amount of photons. The stars and everything begin to look as blue, due again to the Doppler effect. You begin to have trouble discerning what's happening outside, until the usual universe collects into a globe-like figure and compresses to a single dot. This is counterintuitive to the suggestion that since time happens faster outside the black hole, there's a chance that you will observe the universe until its end. But that's just not the case, as was demonstrated by our boys, Copper and Popper. Number 1. Will there be a time when black holes consume all of the universe? It's definitely alarming how this grim question is the most asked question about black holes, but let's tackle it anyway. However, let's ease out that fear and answer it very shortly. The chances of that happening is very small. Why? Because as black holes are effectively powerful vacuum cleaners of the universe, paradoxically speaking, they also leak out mass through something that we call Hawking radiation. So apparently empty space isn't actually empty. It's simply a constant annihilation of virtual particle-antiparticle pairs, which is why conservation laws remain intact. However, at the event horizon of a black hole, this process becomes disrupted. Due to the gravity of a black hole, there's a chance where a particle loses its partner and falls into it. Now our lonely particle won't be annihilated and becomes real, and now has mass that is somehow supplied by the energy from the black hole. In theory, it is possible that if the process continues long enough, a black hole might eventually disappear. That's of course if we follow conservation laws very strictly. Black holes are definitely an interesting bunch, and the more we know about them, the more we discover about our very own universe. But hey, at this point, I want to know more about you guys. What about you? What's the one thing on your mind that bugs you the most about black holes? Let us know by leaving your ideas in the comment section down below. Who knows? Maybe we can make a part 2 of this video using those questions. As I've been telling you always, I couldn't imagine how we would do this without your support. So let me tell you that I'm very thankful for the time you spent for this episode. Did you enjoy the video? Leave us a like so that we can make more of these in the future, or dislike if there are parts that you hated, or if you didn't like the show in general. We can't please everybody, but we can do better next time. If you're a fan of knowledge, particularly knowledge about space and physics, then I'd like to invite you to subscribe to the channel. We make a new episode almost every day, so you would definitely enjoy it during the quarantine period, if you're under one, that is. And hey, if you think our stuff is something that you really find delight in, take the effort further and hit that bell button so that we can notify you whenever a new episode comes up. Until next time, Black Hole fans, stay insanely curious.